We spent $100 million to listen to the universe. We pointed the biggest ears on Earth at the sky and waited. 10 years, maybe more, the result? Nothing. Zero confirmed signals, just static. Just the cosmic microwave background humming like a refrigerator in an empty kitchen. That sounds like a failure. $100 million to hear the galaxy shrug. But here's the thing, that silence is not empty. It's a data point, not a glitch. And according to new math, it's exactly the number we should have expected. Think about what we actually did. The Breakthrough Listen project, funded by a tech billionaire who wanted to know if we're alone, used the Green Bank telescope, the park's observatory, and other massive dishes. They scanned millions of stars. They listened across billions of radio channels. They filtered out interference from cell phones, satellites, and probably someone's microwave reheating leftovers. And after all that, the waveform stayed flat. No alien talk show, no interstellar weather report, no beacon, no ping. Just the universe doing its best impression of someone who didn't want to be found. Most people hear that and think, well, we haven't looked hard enough. The galaxy is big, give it time. But the math says something different. The math says the silence is a measurement. It's a data point that puts a hard ceiling on how many chatty civilizations are out there. And that ceiling is terrifyingly low. To understand why, we have to go back to a lunch conversation in 1950. Enrico Fermi, a physicist who was annoyingly good at estimating things, was talking with friends about flying saucers and faster-than-light travel. The conversation drifted. Then Fermi reportedly blurted out, "Where is everybody?" He wasn't asking about lunch. He was looking at the numbers. Our galaxy has maybe 1 to 400 billion stars. Many of them are older than our sun. If even a tiny fraction had planets, and a tiny fraction of those were habitable, and a tiny fraction of those spawned life, and a tiny fraction of that life got smart enough to build radios, then the galaxy should be crowded. Civilizations should be everywhere. Some of them should have colonized the whole place by now. So where are they? That's the Fermi paradox. Not a joke, not a thought experiment. A genuine contradiction between the apparent likelihood of aliens and the deafening silence. In 1961, a decade after Fermi's lunch, an astronomer named Frank Drake tried to turn the paradox into math. He wrote down an equation, not a physics equation, more like a chain of filters. The Drake equation takes the rate of star formation, multiplies it by the fraction of stars with planets, then multiplies that by the number of habitable planets per star, then by the fraction where life actually starts, then by the fraction where intelligence evolves, then by the fraction that developed detectable technology, and finally by how long those civilizations last. Multiply all those terms together, and you get N, the number of communicating civilizations in the Milky Way right now. It looks scientific. It's got multiplication and everything. But for decades, most of those terms were pure guesswork. You could plug in optimistic numbers and get millions of civilizations. You could plug in pessimistic numbers and get one. Ours, the Drake equation, wasn't a calculator. It was a Rorschach test. It told you more about your own mood than about the galaxy. But here's what changed. In the last few years, scientists stopped guessing. They started measuring. They started building models that replace the old fuzzy terms with hard, tiny numbers. And those numbers are not friendly. They don't give you a crowded galaxy. They give you a galaxy where the nearest civilization might be so far away that their signals haven't reached us yet. Or worse, they might not exist at all. This is where the three filters come in: plate tectonics, oxygen, and geometry. Each one takes the Drake equation and squeezes it like a stress ball. By the end, the number of possible civilizations is so small that Breakthrough Listen's silence stops being a disappointment. It becomes a prediction. The universe told us exactly what we should hear. We just didn't like the answer. Let's start with the first filter. The ground beneath your feet. You probably don't think about plate tectonics. Why would you? It's slow. It's messy. It causes earthquakes and moves continents at the speed your fingernails grow. But according to a 2024 analysis by planetologists Stern and Juriat, plate tectonics might be one of the rarest things in the universe. And they think it's non-negotiable for building a complex civilization. Their argument is simple. If a planet doesn't have shifting continents and long-term tectonic activity, it probably can't support the kind of evolutionary leaps that lead to creatures who build radio telescopes. Why? Because plate tectonics recycles nutrients. It regulates the climate over billions of years. It creates dry land where things can crawl out of the ocean and eventually invent bureaucracy. Without it, you might get a water world. You might get a stagnant crust with no mountains, no erosion, no chemical mixing. You might get life, sure, but you probably don't get complex life. And you definitely don't get fire, metalworking, and Wi-Fi. Stern and Juriat ran the numbers. They added plate tectonics and continents as explicit variables in a Drake-style framework. Their model output was brutal. Less than 0.2% of potentially habitable exoplanets have both continents and long-term plate tectonics. Less than 0.2%. That's 1 in 500. And that's before we even talk about oxygen or brains or radios. That's just the geology filter. You start with a galaxy full of hopeful little worlds in the habitable zone. Then, you apply the tectonics requirement. Most of them vanish. The galaxy goes from a bustling metropolis to a ghost town, and we haven't even gotten to the air yet. So the Drake equation is full of guesses, but new science is replacing those guesses with tiny numbers. The first number is plate tectonics, the second is oxygen, and the third is the geometry of listening itself. Each one makes the silence louder. Each one makes the $100 million quiet more reasonable. And that's where we're going next. So you've got a planet in the habitable zone, right temperature, liquid water, maybe oceans, maybe a nice sky, you're feeling optimistic. You think, great, that's an Earth, that's a candidate. Slow down. Stern and Juriat, two planetologists, looked at that assumption in 2024 and basically said, not so fast. They added a new variable to the Drake-style framework, plate tectonics, and continents. And when they ran the model, the numbers got brutal. Their conclusion: less than 0.2% of those hopeful little worlds have both long-term plate tectonics and actual dry land. Less than 0.2%. That's 1 in 500. 1 in 500. Before we even talk about oxygen or brains or radios. Just the geology filter. Most planets fail the geology test. Why does this matter? Because a planet without plate tectonics is a planet that's geologically dead. It's a stagnant rock. The crust just sits there. No recycling, no mountain building. No deep carbon cycle. The nutrients get locked away. The climate goes haywire over geological time. You might get life, simple life, slimy mats of microbes in a shallow sea. But you don't get the long, complicated evolutionary pressure cooker that produces things like trilobites, let alone things that build particle accelerators. Plate tectonics is the engine that keeps a planet's chemistry mixed. It drags carbon into the mantle and spits it back out through volcanoes. It builds continents, erodes them, and builds them again. It creates coastlines, shallow seas, and 100 different microclimates where evolution can experiment. Without it, you get a smooth, boring water world, a warm bath, maybe some algae, not much else. Stern and Juriat argue that complex life, the kind that eventually invents bureaucracy and radio telescopes, probably requires this geological churn. You need dry land for things to crawl onto. You need erosion to deliver nutrients to the ocean. You need the long-term climate regulation that plate tectonics provides. You need mountains to create rain, shadows, and deserts and forests, and all the diverse pressures that drive natural selection. A stagnant planet doesn't give you that. It gives you a nice, stable, boring extinction. Think of it like a kitchen. A habitable zone planet is the kitchen. It's got the right temperature, the right ingredients. But plate tectonics is the chef. It's the person who actually chops the vegetables, stirs the pot, and occasionally sets something on fire. Without the chef, You've just got a room full of raw ingredients slowly rotting. You can wait 4 billion years. You're not getting a souffle, you're getting mold. Stern and Drya's model is that chef filter. They looked at what we know about planetary formation and geophysics. They factored in the conditions needed for plate tectonics to start and keep going for billions of years. Things like the right amount of water in the mantle, the right crustal composition, the right internal heat budget, and the presence of continents, which themselves require a long history of plate tectonics to form. It's a chicken and egg problem. You need continents to have complex life, but you need plate tectonics to make continents, and you need a very specific planetary recipe to get plate tectonics to run for the entire lifespan of a biosphere. Their model crunched all this, and out came that number, less than 0.2%. Let's visualize this. On screen, the galaxy appears, then dots vanish as we apply the filter. 400 billion stars. Let's say, optimistically, that 1 in 5 has a rocky planet in the habitable zone. That's 80 billion planets. 80 billion. Sounds like a lot. Sounds like a crowded galaxy. Now apply the Stern and Drya filter. Less than 0.2%. Suddenly, your 80 billion hopeful Earths collapse to fewer than 160 million. Still a big number, sure, but we haven't applied any other filters yet. This is just the geology filter. And already, the galaxy has gone from a bustling metropolis of potential civilizations to a sparse scattering of candidates. And those candidates aren't guaranteed to have life. They just have the right geological equipment. They have the chef. The kitchen might still be empty. Now you might ask, is this certain? Is plate tectonics strictly necessary? We only have one example of a planet with life and plate tectonics, and that's Earth. We don't have a second data point. Some scientists argue that maybe other geologies could work. Maybe a planet with massive volcanism, but no plate movement could still recycle nutrients. Maybe a water world could evolve intelligent squid that builds sonar-based technology. These are fun ideas. But Stern and Drya's point is about probability. They're not saying it's impossible for complex life to arise without plate tectonics. They're saying that on Earth, it happened with plate tectonics. And given how long and how specifically Earth's geology has been active, it's reasonable to think that this kind of long-term geological churn is a strong prerequisite. It's not a proof. It's a probability filter. And in the Drake equation, that filter is a number. And their number is very, very small, less than 0.2%. And the continents part is just as important. You can have plate tectonics on a water world. The plates move, but there's no land poking above the surface. You've got a planet-wide ocean with a nice conveyor belt of nutrients. Great for fish, bad for fire. You can't smelt metal underwater. You can't build a radio telescope at the bottom of the sea. You can't discover electricity if you're constantly short-circuiting yourself. Technology, as we know it, requires a dry place to stand and a way to burn things. Continents provide that. They also provide the shallow seas where complex life first experimented with skeletons and shells and eventually crawled onto land. The combination of continents and plate tectonics is what gives you beaches, tidal pools, river deltas, and all the edge environments where evolution gets creative. Stern and Drya bundled continents into their model because they're not automatic. A planet can have plate tectonics and still be a water world if the total water volume is too high or the crust is too thin. Their model screens for both. And the fraction that passes is that brutal 1 in 500. So what does this do to the Fermi paradox? It takes the first big bite out of the optimism. The original Drake equation had a term for the fraction of suitable planets where life actually appears. But Stern and Drya are saying we need to add a term before that. A term for the fraction of habitable zone planets that are even geologically capable of hosting complex life. And that term is tiny. It's a pre-filter. Before you even ask if life can start, you have to ask if the stage is built. And on most planets, the stage is a pile of rubble. The galaxy is full of planets that are the right temperature but the wrong geology. They're like ovens with no heating element. They look the part, but they'll never bake anything. This is a sobering thought. We spent decades hunting for Earth-like planets in habitable zones. We found thousands. We got excited. But Stern and Juria's work suggests that Earth-like means more than just the right orbit. It means a planet that's been geologically alive for billions of years. And that kind of planet is a freak, a cosmic outlier, a geological lottery winner. And we live on one. The implications are already heavy. If you start with the entire galaxy and apply only this filter, the number of potential homes for complex civilizations shrinks dramatically. It makes the silence a little less paradoxical. If most habitable zone planets are geological duds, then the galaxy isn't teeming with civilizations. It's teeming with quiet, dead worlds. Worlds where life might have started but never got past the microbial stage. Worlds where the thermostat broke after 1 billion years and the oceans boiled or froze. Worlds that never got their chef. The Stern and Juria filter is the first mathematical reason to suspect that we might be rare. Not because life is hard to start, but because the right kitchen is hard to find. And this is just the first filter. We haven't even talked about what happens after you get a good kitchen. You still need the right ingredients. You still need the right atmosphere. You still need a long chain of improbable events. The geology filter is just the door. And most planets never walk through it. So geology alone wipes out most habitable planets. The galaxy goes from a hopeful crowd to a near-empty room. But even the lucky ones, the ones with continents and churning plates, face another filter. The next filter is invisible. It's the air. It's oxygen. And it's just as cruel. We just filtered the galaxy by geology. It got quiet. But even the planets that pass, the ones with churning plates and stable continents, face another filter. This one is invisible. You breathe it right now. It's oxygen. And it's a bigger bottleneck than you think. Here's the problem. We assume oxygen is normal. We assume a habitable planet just has it, like a free side salad. But that's wrong. For most of Earth's history, oxygen was a trace gas. For 2 billion years, life bubbled along without much of it. Then, about 2.4 billion years ago, something snapped. The Great Oxidation Event. Cyanobacteria started pumping out oxygen as waste. It poisoned the atmosphere. It killed off most life. It rusted the planet. And it took another 1 billion years for oxygen to reach levels that could support anything more complex than pond scum. We are breathing the exhaust of a billion-year catastrophe. Congratulations, you're alive because of ancient pollution. Now, here's the twist. Frank and Balby 2024 looked at this and asked a brutal question. What if the Great Oxidation Event wasn't inevitable? What if oxygen, at the levels needed for technology, is a freak accident? Their paper, published in Nature Astronomy, proposed the oxygen bottleneck. The idea is simple. A technological civilization needs fire. You can't smelt metal without fire. You can't build engines without fire. You can't even bake bread without fire. And fire needs oxygen. Not a little, a lot. At least 18% atmospheric oxygen to sustain a simple campfire. Below that, you can strike a spark all day. Nothing catches. You're just a monkey with a rock. And here's the thing. Oxygen doesn't just appear. It's not a default setting. It's a product of a very specific geochemical chain. You need photosynthetic life. You need that life to produce oxygen faster than the planet absorbs it. You need oceans that don't immediately react with the oxygen and lock it away in rust. You need continents that weather and bury carbon, preventing it from sucking the oxygen back out. It's a balancing act that lasted billions of years, and it failed on most planets. Most planets never got the Great Oxidation Event. They stayed in a low-oxygen haze, nice for bacteria, useless for engineers. Let's make this concrete. Imagine a planet with perfect tectonics. Continents, oceans, volcanoes, the whole kitchen. But the atmosphere is 2% oxygen. You land there, you step out. You can breathe, no, you choke. But more importantly, you can't light a match. You can't forge iron. You can't build a steam engine. You can't have an industrial revolution. You're stuck in the Stone Age. Forever. That's the oxygen bottleneck. It's not about life, it's about technology. Life can thrive in low oxygen. Technology cannot. So how many planets actually get enough oxygen? Frank and Balbi don't give a single number. They give a probability distribution. And it's not cheerful. Their model suggests that the fraction of habitable zone planets that develop an oxygen-rich atmosphere, one that can support combustion, is tiny. Not 50%, not 10%, more like a few percent, maybe less. And remember, that's after the plate tectonics filter. So you take the 0.2% of planets that have continents and tectonics, then you multiply by the fraction that get enough oxygen. You're now in the realm of 1 in 10,000, 1 in 100,000. And we're not even halfway through the filters. But wait, it gets worse. Because oxygen isn't just rare, it's dangerous. High oxygen atmospheres are chemically aggressive. They corrode, they burn. A planet with 25% oxygen, like Earth today, is a tinderbox. Lightning strikes a forest, it burns. That's good for technology eventually, but it's also a constant threat. Many planets might tip into runaway oxygenation and burn themselves sterile. Or they might cycle back to low oxygen because the carbon burial shuts down. The window for a technological civilization is narrow. You need oxygen levels to stay high for long enough to evolve intelligence, not just a spike. A plateau, Earth managed it for about 400 million years. That's a geological blink, and we're in that blink right now. Let's zoom out. The Fermi paradox often assumes that if a planet is in the habitable zone, it's Earth-like. But Earth-like means more than just the right temperature. It means the right air. And the right air is not guaranteed. It's a tightrope walk. Too little oxygen, no fire. Too much, everything burns. Just right, and you get a civilization that can smelt, forge, and eventually build radio telescopes. But that, just right, is a razor's edge. Frank and Balbi's work shows that the oxygen bottleneck is not a minor hurdle. It's a second great filter. It slashes the number of candidate planets even further, and it's invisible from interstellar distances. We can't measure exoplanet oxygen levels precisely yet, so we look at a planet in the habitable zone and we say maybe. But the math says probably not. Now, combine this with the plate tectonics filter. You have a galaxy full of planets. Most are geological duds. Of the few that have continents and tectonics, most are atmospheric duds. They're stuck in a low oxygen trap. They have oceans. They have land, they might even have life, but they don't have fire. And without fire, they don't have technology. They don't have radio, they don't have starships. They're just quiet biospheres. Beautiful, maybe, full of strange creatures. But silent, they'll never build a transmitter. They'll never answer Fermi's question. They're out there, but they're not talking. This is the point where the optimism starts to crack. We spent decades listening for signals, assuming the galaxy was full of engineers. But the engineers need a very specific planet. A planet that's been geologically alive for billions of years, and then atmospherically juiced with oxygen for hundreds of millions more. That's not common, that's a cosmic lottery win. And we're holding the ticket, but let's be fair. Could there be alternatives? Could a civilization develop technology without oxygen? Frank and Balbi are skeptical. Oxygen is the most efficient chemical oxidizer. It releases a lot of energy per reaction. Other oxidizers, like fluorine or chlorine, are too rare or too violent. You could imagine a civilization using electricity from geothermal or solar without combustion. But to get to that stage, you need an industrial base. And to get an industrial base, you need fire. It's the chicken and egg problem. No fire, no industry. No industry, no advanced energy. You're stuck. The oxygen bottleneck is not a suggestion. It's a hard constraint. Until someone shows us a fluorine-breathing blacksmith, we have to assume oxygen is non-negotiable. So let's do the math again. Start with 100 billion stars in the galaxy. About 20% have habitable zone planets. That's 20 billion. Apply the plate tectonics filter. Less than 0.2%. That's 40 million. Now apply the oxygen bottleneck. Let's be generous and say 1% of those get enough oxygen for technology. That's 400,000. Still a big number, right? 400,000 civilizations in the galaxy sounds crowded. But wait, we haven't applied the time filter. Civilizations don't all arise at the same time. They're spread across billions of years. If a typical technological civilization lasts 10,000 years, then at any given moment, the number of coexisting civilizations is tiny. 400,000 divided by the lifespan of the galaxy. You get maybe a handful, maybe one, maybe zero. And that's with generous numbers. The oxygen bottleneck doesn't just reduce the number of planets. It reduces the number of windows. You need a planet to have oxygen at the right level at the right time. And that window might be geologically short. Earth's oxygen window is about 400 million years wide. That's less than 10% of Earth's history. If intelligence had evolved a few hundred million years earlier, there wouldn't have been enough oxygen. If it evolves a few hundred million years later, the oxygen might be gone, consumed by geological processes. We're not just lucky to have oxygen, we're lucky to be here when it's around. And here's the kicker. We almost missed it. Earth's oxygen levels have fluctuated wildly. During the Carboniferous, oxygen hit 35%, giant insects, constant fires, then it crashed. During the Permian extinction, it dropped below 15%. Most life suffocated. The fact that it stabilized around 21% for the last 50 million years is a statistical miracle. We're breathing a fluke, a happy accident of geology and biology. And that fluke is what allows us to think about Fermi's paradox at all. So what does this mean for SETI? It means that when we point our telescopes at the sky, we're not just looking for planets. We're looking for planets that survived a billion-year geological obstacle course, and then got an oxygen transfusion at the right time. That's a very small target. And even if such a planet exists, even if a civilization is broadcasting right now, we still have to catch the signal. That's the next filter, geometry. But before we go there, let's sit with this for a moment. The oxygen bottleneck is cruel because it's invisible. We can see continents through advanced telescopes. We can maybe detect plate tectonics through atmospheric biosignatures. But oxygen, we can measure it, but we can't know if it's been there long enough. A planet might have oxygen today, but it might have just gotten it. The civilization might be a billion years away, or it might have already lost it. The signal we're looking for is not just a planet. It's a planet at the right moment. And the moment is fleeting. Combine tectonics and oxygen, and the galaxy is mostly sterile, not dead. Sterile, there's a difference. Dead means nothing lives. Sterile means nothing talks. The galaxy could be teeming with life. Oceans of algae. Forests of strange trees. Creatures that sing and hunt and dream. But they can't build a radio. They can't leave their planet. They can't answer. They're in the dark, looking up at the same stars, wondering the same thing. Are we alone? And they'll never know because they can't light a fire. That's the oxygen bottleneck. It's not a wall, it's a ceiling, low enough that most planets never break through, high enough that we, by sheer accident, poked our heads above it. And now we're looking around, expecting to see others. But the room is empty, not because no one's home, because no one else could climb. Now, if a civilization does exist, if it somehow cleared both the geological and atmospheric hurdles, can we hear it? That's the next question. And the answer is geometry, pure, unforgiving geometry. Now, even if a civilization clears both the geological and atmospheric hurdles, we still have to catch their signal. That's the next filter, geometry. Pure, unforgiving geometry. In May 2025, a researcher named Sivalti dropped a preprint on RZiv. The title was technical. The math was simple. The conclusion was brutal. He built a geometric model of passive SETI. Passive means we're just listening, not shouting into the void. just holding a tin can to the cosmos and hoping. His model asks one question. If a civilization is out there, transmitting, what are the odds we actually hear it? The answer is a formula. P equals about 0.6 times delta over R. Let's unpack that. P is the probability of detecting at least one signal. Delta is the distance between the transmitter and our receiver. R is the radius of the Milky Way galaxy, about 50,000 light-years. So the probability of hearing someone depends on how close they are. If they're next door, delta is small, P is small. We might miss them anyway. If they're far away, delta is huge. P gets bigger, but for a sad reason. Wait, that sounds backwards. Shouldn't closer aliens be easier to hear? Yes, in real life. But the formula isn't measuring signal strength. It's measuring the chance that our listening bubble overlaps with their transmission bubble. It's a geometry problem. Imagine the galaxy as a giant dark field. You're standing in one spot, holding a flashlight. The alien is somewhere else, holding a flashlight. You're both spinning around randomly, flicking the lights on and off. What are the odds your beams cross? That's Civalti's model. The probability of intersection scales with the distance between you, not because distant lights are brighter, but because the farther apart you are, the more space there is for your beams to miss each other. Wait again, that still sounds weird. Let's do it properly. Picture the galaxy as a circle. You are a dot on the edge, the alien is another dot. You both send out signals in random directions. The probability your signal sweeps over the alien is tiny. The probability their signal sweeps over you is tiny. The probability both happen at the same time is tinier still. Civalti's formula approximates the combined probability. It ends up proportional to delta over R if the alien is on the other side of the galaxy. Delta is roughly R, the probability is around 0.6. Sounds high. But that's a best-case scenario, and it's a trap. Because if the alien is on the other side of the galaxy, the signal travel time is 50,000 years. You broadcast. They receive it 50 millennia later. They reply. Another 50 millennia. Your great-great-great-grand receivers might get the ping. That's not a conversation. That's a fossil. Now, the real killer. If civilizations are rare, delta is huge. If delta is huge, P is not small. P is irrelevant. Because the signal is so old, the civilization might be dead. Or we're dead. Or the signal is so faint, it's below noise. The formula assumes ideal detection, perfect receivers, infinite sensitivity. In reality, our telescopes have limits. Breakthrough Listen can hear a strong signal from maybe 1,000 light-years away. Maybe if the transmitter is pointed right at us, if the frequency is clear, if we're listening at the right time, the actual probability of detection is much lower than the geometric ideal. Much, much lower. Let's put numbers on it. Suppose there are 100 civilizations in the galaxy. Sounds like a lot. But the galaxy has 100 billion stars. That's one civilization per billion stars. The average distance between them, thousands of light-years. Delta is huge. The geometric probability of overlapping beams is maybe a few percent. Then you multiply by the chance they're transmitting when we're listening. Multiply by the chance they use radio. Multiply by the chance their signal isn't blocked by space dust. Multiply by the chance we point the telescope exactly right. The final probability is a rounding error. Breakthrough Listen has looked at millions of stars. It's the biggest SETI project ever. $100 million, the best equipment. A decade of staring, and it heard nothing. Civalti's model says that's not a surprise. It's exactly what you'd expect if civilizations are rare. If the nearest one is tens of thousands of light-years away, the geometric probability of detection is effectively zero. Not because they're not transmitting, because the galaxy is too big and we're too far apart. Let's make this stupidly concrete. You're in New York, your friend is in Tokyo, you both have walkie-talkies. You agree to turn them on for 1 minute at a random time each day. What are the odds you hear each other? Near zero. Not because the walkie-talkies don't work, Because the timing and distance and power are all wrong. Now imagine you don't even know your friend exists. You don't know the channel, you don't know the time, you don't even know if they own a walkie-talkie. That's SETI. Now scale it up. New York to Tokyo is 12,000 kilometers. The galaxy is 50,000 light years. 1 light year is about 10 trillion kilometers. The galaxy is 500 quadrillion kilometers across. Your walkie-talkie has a range of 2 kilometers. You're standing in a field, spinning, hitting the talk button, hoping. That's the geometric filter. It's not about technology. It's about space being too big. It's about time being too long. It's about 2 tiny bubbles in an ocean of nothing, trying to touch. And here's the worst part. SETI's model assumes civilizations are broadcasting forever. Continuous, isotropic, eternal signals. But they're probably not. Civilizations might broadcast for a few hundred years. Then they go quiet. Or they switch to something we can't detect. Or they die. The window is tiny. The galaxy is ancient. The chance of overlapping in time is even smaller than overlapping in space. So the effective delta isn't just distance. It's distance plus time, a 4-dimensional needle in a haystack. The formula P equals 0.6 delta over R is optimistic. It assumes the signals are there, loud, and forever. Real life is worse, much worse. So what does this mean for Breakthrough Listen? The silence is not a failure of the search. It's a success of prediction. If civilizations are rare, the geometric model says we should hear nothing. And we heard nothing. The null result is a data point. It tells us delta is probably huge. The nearest civilization is far, very far, or they're not transmitting, or they don't exist. The geometry doesn't care which. It just multiplies the odds down to a shrug. You can have 1 million civilizations in the galaxy. If they're spread out, the probability of detecting any one of them is still tiny. Because the galaxy is 100,000 light years across. Our best telescopes can scan a bubble a few thousand light years wide. That's a fraction of a percent of the galaxy's volume. We're not listening to the galaxy. We're listening to our local neighborhood. And the neighborhood is quiet. That's the geometric filter. It's the final punch. First, plate tectonics wipes out most planets. Then oxygen wipes out most of the rest. Then geometry wipes out the rest of the rest. Multiply them together. The expected number of detectable civilizations is a number so small, it might as well be 0. Breakthrough Listen's silence was predicted. Not by cynics, by math. The universe is not refusing to talk. It's just too big for the conversation. And we're standing in a corner, holding a tin can, waiting for a voice that might never come. We've walked through 3 separate filters. Each one, on its own, already makes the galaxy look emptier than we thought. Now we have to combine them. And combining them is not addition. It's multiplication. And multiplication of small numbers gets small fast. Really fast. Let's do it. Start with the Drake equation. The original framework had terms for star formation, fraction of stars with planets, number of habitable planets, fraction where life emerges, fraction where intelligence evolves, fraction that developed technology, and lifetime of that civilization. 7 terms, most of them were pure guesses. Optimists plugged in hopeful numbers and got millions of civilizations. Pessimists plugged in cautious numbers and got one. Us. That's the old game. Now we have new numbers for 3 of those terms. Not guesses, models, published models, and they all point down. Stern and Juriat looked at the fraction of habitable planets that actually have continents and long-term plate tectonics. Their number, less than 0.2%. Let's write that as a decimal. 0.002, that's the geology filter. Frank and Balbi looked at the fraction of those planets that build up enough oxygen for a technological civilization. They didn't give a single clean number because the geochemistry is complicated, but their analysis suggests it's another severe cut. Maybe 1 in 10, maybe 1 in 100. Let's be generous. Say 1 in 10, 0.1. Now SETI's geometric model. This one is different. It doesn't reduce the number of civilizations. It reduces the probability we detect them, even if they exist. The formula, probability of detection, is roughly 0.6 times delta over r. Delta is the distance to the nearest transmitting civilization. R is the radius of the galaxy. If civilizations are rare, delta is huge. If delta is, say, 30,000 light-years and r is 50,000 light-years, then delta over r is 0.6. Multiply by 0.6. You get a detection probability around 0.36. That's if they're broadcasting powerfully, continuously, and we're pointed the right way. But if they're farther, delta goes up. If they're not broadcasting continuously, the effective probability drops further. If they're using directional beams we're not in line with, it drops further. The model's 0.6 factor is already optimistic. It assumes isotropic signals, perfect reception, and eternal transmission. Real life is worse, so the detection probability is not a constant. It's a function of how alone we are. And if we're very alone, that function crushes the odds. Now multiply. Let's be absurdly generous. Assume the original Drake equation, without these filters, gave an optimistic n of 1 million civilizations. 1 million. Sounds like a party. Now apply the geology filter. 0.002 times 1 million. That's 2,000. Already the party is a small town. Apply the oxygen bottleneck. Generously, 1 in 10, 200. Now the party is a wedding reception where nobody knows each other. Apply the geometric detection filter. If the nearest civilization is tens of thousands of light-years away, detection probability might be 1 in 3, 1 in 10, worse. Suddenly, even if 200 civilizations exist, we might detect none of them. 0. The silence is not a mystery. The silence is the expected output of the math. Breakthrough Listen spent $100 million and 10 years listening, and heard nothing. That nothing is a measurement. It tells us that the product of those filters is small, very small. It doesn't tell us exactly how small, but it puts an upper bound. The number of detectable civilizations in our galaxy right now is consistent with 0. Maybe it is 0, maybe it's 1, us. Maybe it's a handful, but they're so far away that our best instruments are effectively deaf. All three are mathematically almost the same thing. Here's another way to think about it. Imagine you're in a huge dark warehouse. You have a flashlight, you shine it around, you see nothing. Does that mean the warehouse is empty? No, it means your flashlight reaches 50 feet and the warehouse is 1,000 feet across. If there's someone else in there, and they're standing at the far end, you won't see them. You won't hear them unless they scream. And if they're not screaming, you get silence. The silence doesn't prove you're alone. It proves the warehouse is big and your flashlight is small. Now make the warehouse 100,000 light-years across. Make the flashlight breakthrough listen. Make the scream a powerful radio transmission aimed right at us. And make the other person a civilization that needs plate tectonics, continents, and an oxygen atmosphere to even exist. Suddenly, the silence is not surprising. It's inevitable. The silence is the sound of a warehouse too big for flashlights. Now let's get more precise about what the silence actually measures. In physics, a null result is still a result. If you build a detector to look for a particle and you see nothing, you haven't failed. You've placed an upper limit on how often that particle interacts with your detector. Same here. Breakthrough Listen is a detector. It's looking for narrowband radio signals that can't be natural. It scanned millions of stars. It scanned the galactic plane. It scanned nearby galaxies. It found 0 confirmed signals. 0? That doesn't mean aliens don't exist. It means the number of civilizations transmitting in the right way, at the right time, in the right direction, within our detection volume, is very low. We can quantify that. If the galaxy had 1 million civilizations broadcasting continuously, our detection probability would be high. We'd likely have heard something. The fact we heard nothing tells us the number is far below 1 million. How far? Depends on the model. but the geometric model says if n is small, detection is unlikely. So the null result is consistent with n being small. It's a self-consistent loop. The math predicts silence. The observation is silence. The observation supports the math. That's how science works. You make a prediction, you test it, and the result either matches or it doesn't. Here, it matches. The prediction was, if these filters are real, we should hear nothing. We heard nothing. That doesn't prove the filters are correct, but it means the filters survive this test. They're not falsified. And that's progress. Before these models, the silence was just awkward. Now it's a data point with a confidence interval, a fuzzy one, but a real one. Let's talk about what this does to the Drake equation emotionally. Because the Drake equation has always been a Rorschach test. You look at it and see what you want to see. Optimists see a galaxy full of friends. Pessimists see a lonely rock. Now the new terms are forcing a specific answer. Not a precise number, but a direction, down. The geology filter pushes down. The oxygen filter pushes down. The geometric filter pushes down the detection probability. Multiply them, and the expected n is a number so small it rounds to 0 in most casual conversations. That's not nihilism, that's just arithmetic, and it reframes the entire Fermi paradox. The paradox was, they should be here, so where are they? The new math says they shouldn't be here. The expectation was wrong. The paradox dissolves. Fermi's question wasn't wrong. The assumption behind it was. The assumption that the galaxy should be teeming, that complex life is common, that technology is a natural outcome, that signals should be everywhere. Every one of those assumptions now has a mathematical counterargument. Published, modeled, testable. The silence is not a failure of imagination, it's a success of prediction. Now, a caveat. These models are new. Savalti's paper is a preprint, not yet peer-reviewed. Stern and Juria's work was reported via a science news site. Frank and Balbai's is in a top journal, but the oxygen bottleneck is still a hypothesis. None of this is settled, but it's the direction, the numbers are moving. And breakthrough listens, silence pushes them further in that direction. Every year of silence tightens the upper bound. We are running a real-time experiment on galactic loneliness, and the results are coming in. Quietly. So what's the synthesis? The silence is a measurement. It tells us the number of detectable civilizations is low. The geology filter tells us why it might be low. The oxygen filter tells us why it might be even lower. The geometric filter tells us why, even if it's not 0, we still might not hear them. Together, they turn the Fermi paradox from a philosophical shrug into a quantitative statement. The statement is, we are either first, last, or very far from anyone else. And those three options are mathematically almost identical from the perspective of a radio telescope. Let that sink in. The most expensive SETI project in history has given us a result, not a signal, a bound, a number that frames our existence. The universe is not refusing to talk. It's just that the chances of a conversation were always astronomically small, and we're only now building the math to prove it. So what does that mean for us? For the way we think about ourselves? For the way we think about the search? That's where we go next. The universe gave us its answer by staying silent. That's not a metaphor, that's a data point. And it's the most honest answer we have. So where does that leave us? It leaves us with 3 options, and they're all mathematically almost identical. Option 1, we are first. The first technological civilization in the galaxy, or at least the first one close enough to matter. Someone has to be first. Maybe it's us, that's not arrogance. That's just probability doing its job. If the filters are as tight as the models suggest, then the expected number of civilizations is less than 1, which means the most likely number is 0. And if it's not 0, it's 1. And we're it, congratulations, you're the first. The galaxy is a silent, empty stage, and we just walked on, no applause, just the hum of a microwave. Option 2, we are last. Everyone else came and went. They rose, they built, they broadcast, and then they collapsed. Or got quiet. or never made it past their own oxygen bottleneck. Their signals passed us while we were still figuring out fire, or they haven't reached us yet, or we just missed them. The window for detection is small. Civilty's model assumes continuous transmission, but real civilizations don't broadcast forever. They go silent. They die. They move on to something we can't hear. If the average lifetime of a technological civilization is a few thousand years, and the galaxy is 10 billion years old, then the chances of two windows overlapping are vanishingly small. We're not listening to a crowded room. We're listening to a graveyard, and the last one died 1 million years ago. Option 3, we are isolated, not first, not last, just far. The nearest civilization is out there, but it's thousands of light years away. Their signals are too weak. Our receivers are too small. The geometry just doesn't work. Remember the formula. P equals about 0.6 delta over r if delta is 10,000 light years and r is 50,000 light years. P is about 0.12. That's a 12% chance of detection. If they're transmitting at the right frequency, in the right direction, at the right time, and we're listening. And that's for one civilization. If there are 10 civilizations scattered randomly, the nearest one might still be 10,000 light years away. And the probability of detecting any of them doesn't add up nicely. It's not 10 times 12%. It's a complicated integral over random positions. Civilty's model shows that even with dozens of civilizations, the detection probability can stay below 50%. The galaxy is big. Radio waves get weak. The inverse square law is unforgiving. A signal from 1,000 light years away is 1 million times weaker than the same signal from 1 light year away. Breakthrough listen is sensitive, but not that sensitive. We're listening for a whisper across an ocean, and the ocean is mostly empty. So those are the options. First, last, or impossibly far. And here's the thing. From the perspective of a radio telescope, they all look exactly the same. Silence, the same flat waveform, the same null result, the same zero. You can't tell the difference between an empty galaxy, a dead galaxy, and a galaxy where everyone is just too far away. The silence is ambiguous, but it's not meaningless. It's a bound, it's a measurement. It tells us the number of detectable civilizations is low, very low, maybe zero. And that changes how we think about ourselves. For most of human history, we assumed we were special. The center of the universe, the pinnacle of creation. Then Copernicus came along and said, actually, you're just a rock orbiting a star. Then Darwin said, actually, you're just a monkey with anxiety. Then Hubble said, actually, your galaxy is one of trillions. Each time we got less special, more average, more insignificant. The Copernican principle says we should assume we're typical. Nothing special about our position, our time, or our planet. That principle has been a good guide. It works for stars, galaxies, and physics. But the Fermi paradox and the new math suggest something different. Maybe the Copernican principle fails for life. Maybe we're not typical. Maybe we're a freak. A geological freak on a planet with just the right amount of water, just the right amount of tectonics, just the right amount of oxygen, just the right amount of time. Maybe complex life is so rare that we're the only example in the galaxy. That's not mysticism. That's just multiplying small numbers. If the probability of plate tectonics is 0.002, and the probability of an oxygen atmosphere is 0.01, and the probability of intelligence is 0.001, and the probability of technology is 0.1, then the expected number of civilizations is something like 0.0000002. That's not a number, that's a rounding error. And if that's true, then we're not just another rock. We're the rock. The one rock where everything lined up. That's either terrifying or comforting, depending on your mood. Terrifying because if we mess this up, there's no backup. No galactic federation to save us. No older, wiser species to guide us. We're it, the only conscious corner of the galaxy. If we burn the planet, if we nuke ourselves, if we choke on our own exhaust, the galaxy goes dark again. Permanently. That's a lot of pressure. Comforting because if we're alone, we can stop worrying about alien invasions. No one is coming to eat us, colonize us, or judge our reality TV. The silence means safety. Lonely, but safe. And there's a strange dignity in being the first. Someone has to be, why not us? But there's another layer. Even if we're not alone, even if there are others out there, the silence tells us something about them. They're not talking, or they can't talk, or they're talking in a way we can't hear. Maybe they're using lasers. Maybe they're using neutrinos. Maybe they're using something we haven't invented yet. Maybe they're deliberately quiet. Maybe they've learned something we haven't. Maybe the galaxy is full of life, but everyone is hiding. That's the dark forest hypothesis. The idea that the universe is a dangerous place and anyone who broadcasts gets eaten. So everyone stays quiet. It's a fun idea for science fiction, but it's not testable. And it violates the Copernican principle again. It assumes everyone behaves the same way. Everyone is paranoid. Everyone is hiding. That's a strong assumption. The math doesn't need it. The math just says the chances are low. No conspiracy required. Just cold, hard probability. So what do we do with this information? Do we stop searching? No. Breakthrough listen continues. New telescopes are being built. The square-kilometer array will be even more sensitive. We'll keep listening. But we should adjust our expectations. The silence is not a failure. It's a success of prediction. We built a model and the data matched. That's how science works. You make a hypothesis, you test it, and you update your beliefs. Our hypothesis was that the galaxy might be crowded. We tested it. The data said no, so we update. The galaxy is not crowded. It's empty, or nearly empty. And that's interesting. That's worth knowing. The search itself has value. Even if we never find a signal, we're learning something. We're learning about planetary geology, atmospheric chemistry, and the limits of detection. We're learning about ourselves. The Fermi paradox forces us to confront our own fragility. If civilizations are rare, then we're precious. If they're common but short-lived, then we're in danger. If they're common but quiet, then we're missing something. Each possibility is a lesson. And the lesson right now is humility. The universe is not refusing to talk. It's just that the chances of a conversation were always astronomically small. And we're only now building the math to prove it. So the next time someone asks, where is everybody, you can say, about 0.6 delta over R, and that means almost certainly not here. Let that sit for a moment. We spent $100 million, pointed the world's best ears at the sky, and heard nothing. And that nothing is the most important SETI result ever. It's a number. It's a bound. It's a measurement of our solitude. We are either first, last, or very far from anyone else. And those three options are mathematically almost identical. The same silence, the same zero, the same flat waveform, but now the zero has meaning. It's not an absence of information. It's a presence of constraint. The universe told us something. It told us we're rare, maybe unique, maybe the only ones, and that's not a sad answer. It's a precise one. The silence itself is the data. So let's go back to the microwave. We started this whole thing with a microwave sitting on a counter, waiting for a beep that never comes. And now, after all the math, after the plate tectonics, the oxygen, the geometry, the $100 million, the decade of listening, the microwave is still there. Still silent. But it's not the same microwave anymore. It's not just an appliance, it's a monument. A monument to the most expensive, most rigorous, most honest answer humanity has ever gotten to the biggest question we can ask. Are we alone? And the answer, after all of that, is a number. About 0.6 delta over R. Which for our galaxy, for our receivers, for our moment in time, rounds to zero. That's the answer. Zero, but not an empty zero, not a shrug, not a glitch. A measured zero. A zero with error bars. A zero that cost $100 million to confirm. A zero that tells us something. The universe is not full of chatty neighbors. It's not a crowded party we weren't invited to. It's a vast, cold, mostly empty room. And we're in one corner, holding a radio, hearing static. And that static is the sound of the universe telling us the truth, not the truth we wanted, the truth that is, and there's something deeply weird about that, something almost funny. We built the biggest ears in history. We pointed them at the sky. We filtered out the noise. We waited. And the universe said nothing, not because it's hiding something, not because we're not listening hard enough, but because there's probably no one there. Or if there is, they're so far away that their signals haven't reached us, and won't reach us, not in our lifetimes, not in 1,000 lifetimes, not in the lifetime of our species. The distances are just too big. The probabilities are just too small. The filters are just too tight. Plate tectonics wipes out most of the candidates. Oxygen wipes out most of the rest. Geometry wipes out the detection. Multiply them together, and you get a number so close to zero that calling it zero isn't rounding. It's honesty. And here's the thing, we've known this was possible for decades. Fermi knew it. Drake knew it. The early SETI pioneers knew it. They knew the silence was the most likely outcome. But they listened anyway, not because they expected to hear something, but because not listening was worse. Not listening meant assuming. Not listening meant guessing. Not listening meant never knowing if the microwave was broken or if the kitchen was empty. Now we know. The kitchen is empty, or at least our corner of it is. And that knowledge is worth the $100 million. It's worth the decades of work. It's worth the quiet disappointment. Because now we can stop guessing. Now we can update our beliefs. Now we can look at the Drake equation and fill in some of those terms with actual numbers instead of wishful thinking. And those numbers are small. Really small. Uncomfortably small. The kind of small that makes you feel a little dizzy if you think about it too long. We are either the first technological civilization in the galaxy, or the last, or the only one that will ever exist. Those are the options. First, last, or alone. And mathematically, they're almost identical. All three produce the same silence, the same flat waveform, the same zero. But now the zero has a story. It's not just an absence of signal. It's a measurement of our context. It's a coordinate on a map of possibilities. It's a data point in the biggest experiment ever run, the experiment called existence. And the result is we're rare, maybe unique, maybe the only ones. And that's not a sad answer. It's not a happy answer either. It's just the answer. The one the math gave us. The one the microwave confirmed. The one we have to live with. So what do we do with that? What do we do with the knowledge that we're probably alone? Do we panic? Do we celebrate? Do we start building a backup civilization on Mars just in case? Probably that last one. But more importantly, we keep looking. Not because we expect to find something now, but because looking is what we do. It's what we've always done. We looked at the stars and wondered. We built tools to see them better. We built tools to hear them. We built equations to understand them. And those equations, those tools, that wondering, they changed us. They made us more careful, more precise, more humble. They forced us to confront the possibility that we are not the center of the universe, but we might be the only ones in it who can ask the question. That's a heavy responsibility. If we're the only ones, then we're the universe's only chance to be understood. The only chance for the carbon, the water, the starlight to look back at itself and say, I am here. That's not nothing, that's everything. And if we're not the only ones, if there's someone else out there, somewhere in the galaxy, also listening, also waiting, also wondering, then our silence is their silence too. They're sitting in their own kitchen, staring at their own equivalent of a microwave, hearing nothing. And they're doing the same math. They're multiplying the same filters. They're arriving at the same zero. And they're feeling the same mix of awe and loneliness. And maybe that's the real answer to the Fermi paradox. Not that we're alone, not that we're first or last, but that the distances between minds are so vast, the windows of time so narrow, the conditions so rare, that that every civilization that ever exists will face the same silence. And the only way to break it is to keep listening, to keep transmitting, to keep being the kind of species that doesn't give up just because the math is discouraging. Because the math was always discouraging. The math was always pointing to 0, but we did it anyway. We spent the money, we built the dishes, we wrote the code, we waited, and we got an answer. Not the one we wanted, but an answer. And that's more than we had before. So the next time you're in your kitchen and you glance at your microwave and you notice it's not beeping, remember what that silence means. It's not a failure, it's not a broken appliance. It's not even a metaphor anymore, it's a fact. The galaxy is quiet. We are either first or last or very, very far from anyone else. And that's okay, that's more than okay. That's knowledge, that's progress. That's the universe speaking by not speaking. And that's the most honest answer we have. Thanks for listening. Now go check your leftovers.